Alright, so let's talk about the incenter now. And the incenter, for a general introduction, is where, let's say you have a general triangle. I'm drawing an acute triangle right now. You can try to you can try this with obtuse as well. It gives you the same result. So let's say you have a triangle ABC. Now, what you do is you draw angle bisectors for all the three angles. So let's say this is the angle bisector for B, this is the angle bisector for A, and this is the angle bisector for C. By Euclidean geometry, we know that all of these three angle bisectors intersect at one point, and you can see the proof for that as well. And that point of intersection is called as the incenter. Now, what we can do is from the incenter, we can draw with the incenter as the center of a circle, and the radius as any of the distance is perpendicular distance from the incenter to the sides. We can draw what's called as the incircle. So that's what the incenter is. Now, how do we write the coordinates of the incenter? So let me draw a better triangle. So let's say this is the first side, this is the second side, and this is the third side. All right. And I draw the angle bisector for angle A. So let's say this is that. Let's say it intersects BC, the side BC, on point D. And let's say the angle bisector for angle B, let's say that it intersects AD at the incenter, which we are calling as I. All right, so bunch of just obvious facts. Both of these angles are equal, and both of these angles are equal. All right, and let us also name the coordinates of these sides of these vertices. So A is x1 comma y1, B is x2 comma y2, C is x3 comma y3. Standard convention, nothing special. The side opposite to vertex A, we will call that as the side length as small a. The side opposite to vertex B, we'll call that as small b. This will be small c. Let's try to figure out the coordinates of the incenter. So whenever we are working with triangle centers, the main idea is to use the section formula. And the section formula, since we have general coordinates, if we somehow figure out a nice enough ratio between these coordinates, the ratio of division, we can write the coordinates of the triangle centers as well. The thing that comes to our rescue with incenters is the angle bisector theorem, and I'll just state the angle bisector theorem with a short proof. The angle bisector theorem really is that, let's say you have another triangle. We are drawing many triangles today, by the way. Let's say this is A, B, C, and the angle bisector intersects at point D. Then you can write that the side length BD over BC or over DC. Let me change that over DC. This is equal to the side length that is corresponding the actual side length of the triangle. So BD corresponds to AB, and DC corresponds to AC. You can also write this as what? AB will be side small c, and AC will be side small b. This is the angle bisector theorem. How do you prove this? Well, let's see. What we can do is we can write using the sine rule, and I'm going to give this a very short proof since that's not the purpose of this video. But anyways, using sine rule, we can write sine of angle BAD, that's this one, sine angle BAD divided by the sine of angle B meaning this entire angle, is equal to the side opposite to angle BAD is BD, and the side opposite to angle B is AD. Similarly, in the other half, not exactly half, but the other bisected half, angle bisected half, you can write sine of angle DAC divided by sine of angle C is equal to opposite to angle DAC you have side DC, and opposite to angle C you have AD. Now what you can do is you can divide both of these, and since angle BAD and DAC are equal, remember, bisectors. So since they're equal, the numerators in both of these fractions are the same. So if you divide both of these equations, let's say you divide equation 1 divided by equation 2, you get sine of angle C divided by sine of angle B is equal to DC by AD into AD by BD. You cancel the ADs because they're the same thing, and you get DC by BD. So DC by BD. That's okay. And also, since B and C are themselves a part of triangle ABC, using the sine rule again, we can write this as small c over small b. Opposite to angle C, you have the side small c, and opposite to angle B, you have the side small b. So yeah, I guess I've not committed any major mistakes. So we divided equation 1 by equation 2. Oh, okay. So that's a problem. This had to be angle B over angle C. Sorry. So this will be B over C, and this is the same thing. If you notice, this is the same thing. All right. Angle bisector theorem. So that's the angle bisector theorem. Let me just remove that for now, since it's not really relevant again. We'll just keep the statement of the theorem for our perusal, and we'll remove the proof part. So let's try to first figure out the coordinates of point D, since then we can go on to find the coordinates of I by again finding some sort of a ratio. So we know that BD over DC is equal to C over B. So this means that D divides BC in the ratio C is to B, in the ratio C is to B. And B here is x2, y2, and C is x3, y3. And using the section formula, you can write the coordinates of D to be C times the second one. So C times x3 plus B times the first one. So that's B times x2 divided by B plus C. And then for the y coordinate, just the same thing. So cy3 plus by2 divided by b plus c. Okay, so we figured out what D is. Now let's try to figure out what I will be. If you look closely, then in this triangle ABD, this side, this length BI bisects the angle B. So you can again apply the angle bisector theorem in this triangle, in the triangle ABD. What you can write now is that ID over IA, again, I'm not writing directed line segments, by the way, so ignore the weird nomenclature. But anyways, these lens, the ratio of these lens is equal to the ratio of the corresponding sides of the triangle. So ID corresponds to BD, and IA corresponds to AB. So that's side C. What is the length of BD? Since we want to write a proper ratio and we have already used the side lengths of the triangle here, let's just try to write BD in a more appropriate form. So we know that BD over DC is C over B, and that BD plus DC is the side BC, and that's equal to A. Now this is a simple linear equation in one variable type of problem. You can write BD is equal to C times A over B plus C. All right. So once you take this, you plug it right here. This gives you A over B plus C. Notice the C's get canceled out. Anyways, so I now divides, let me write this here. I divides AD in the ratio. The ratio is IA is to ID, so the opposite of it. So IA is B plus C is to A. So this is the ratio. And we know what the coordinates of A are. They are x1, y1, and D is just this. Now we just need to apply the section formula right again. So I now is equal to the first ratio, the first part of the ratio, multiplied by D, the second point, So b plus c times cx3 plus bx2 divided by b plus c plus a times the first one, so ax1 divided by the sum of both of these, so a plus b plus c. Similarly for y, so notice b plus c just cancels out, and similarly for y, you can write ay1 plus by2 plus cy3 divided by a plus b plus c. Hence, this is the coordinate of, these are the coordinates of the incenter for a triangle that's defined like this. The incenter, let me just write it again, the incenter is going to be equal to ax1 plus bx2 plus cx3 divided by a plus b plus c. A, b, c are the side lengths, and the y-coordinate is just, well, almost the same. Instead of the x's, you write the y's, so ay1 plus by2 plus cy3 divided by a plus b plus c. See you in the next video.